November 2023. The most profound questions in cosmology aren't just about what's the universe, but how it managed to at all. Cosmologists at institutions like Perimeter Institute, CERN, and Caltech grapple with a question that melts intuition and challenges the very bedrock of scientific understanding. How did the universe begin from absolute nothingness? This isn't a mere philosophical musings for late-night debates. It is a fundamental paradox woven into the fabric of existence, a cosmic riddle that demands a scientific answer. Textbooks, the very pillars of our understanding, demand energy conservation. They assert that energy cannot be created or destroyed, only transformed. Every observable phenomenon, every interaction, every particle seemingly requires a source, an antecedent, a prior state from which it emerged. Yet, here we are, immersed in a universe teeming with mass, energy, and spacetime itself. Billions of galaxies, each containing billions of stars, radiating unimaginable power. Vast cosmic structures, dark matter halos, the intricate dance of fundamental forces, all of it undeniably present. Where did it all come from? What was the initial deposit that funded this colossal cosmic enterprise? The tension is palpable. Classical physics, with its elegant equations and predictable causality, screams impossibility. It insists that something cannot arise from nothing without violating the most sacred laws of nature. A vacuum, in the classical sense, is an inert, empty expanse, a state of absolute non-being. For a universe to spontaneously ignite from such a void feels less like science and more like magic. Yet, the universe here. This isn't a speculative theory. It's the most profound, time-stamped observation we have, the existence of everything. For centuries, this question was relegated to the realm of philosophy or theology. But frontier science, armed with increasingly sophisticated instruments and revolutionary theories, has begun to pry open this ultimate mystery. We are not just asking, it happened, but the stakes couldn't be higher. Understanding the genesis of the cosmos isn't just about satisfying intellectual curiosity. It's about comprehending our place within it, the fundamental nature of reality, and the very limits of what science can explain. If the universe truly sprang from nothing, it redefines our understanding of creation, causality, and even the concept of nothing itself. Consider the sheer scale of the universe's inventory. An estimated 10 to the 80 protons, an equivalent number of electrons, a vast ocean of photons, neutrinos, and the mysterious dark matter and dark energy that dominate its composition. This represents an astronomical amount of positive mass energy. If the universe began from nothing, where did all this energy come from? It's as if an unimaginably vast bank account suddenly materialized, filled with cosmic currency with no prior deposit. This is the universe's impossible debt, a cosmic IOU of unimaginable proportions. But what if the quantum realm, that bizarre, counterintuitive domain where particles can be in multiple places at once and observation fundamentally alters reality, offers a loophole? What if the rules that govern the macroscopic world, the world of planets and stars and people, don't apply universally to the very genesis of existence? Perhaps the concept of nothingness itself, when viewed through the lens of quantum mechanics, is far more complex, far more pregnant with potential than classical intuition allows. The very notion of a vacuum in quantum field theory is radically different from its classical counterpart. It's not empty, inert space, but a seething, effervescent cauldron of potential. Could this quantum vacuum, this vibrant non-being, be the source code, the primordial font from which everything we know burst forth? Could the universe be a spontaneous, self-sustaining fluctuation, a magnificent cosmic bubble that borrowed its very existence into being? This isn't a retreat into mysticism. It's a bold leap into the unknown, guided by the mathematics of quantum gravity and the observations of distant galaxies. It's the pursuit of a scientific explanation for the ultimate magic trick. If the universe truly did begin from a state of absolute non-existence, then the most fundamental law of physics, the conservation of energy, must have been circumvented or perhaps redefined. This isn't about breaking the rules. It's about discovering the deeper, more elegant rules that permit such an audacious act of creation. The question isn't whether the universe exists without a prior cause, but rather what intricate hidden mechanisms allow it to do so while ultimately upholding a grander cosmic balance. What kind of cosmic IOU could possibly fund such a vast, enduring reality? And how, in the vast ledger of spacetime, is this impossible debt being managed, perhaps even repaid? The answer, as we shall see, takes us beyond mere particles and forces into the very architecture of spacetime and the audacious financial maneuvering of the cosmos itself. Building on that cosmic riddle, the universe's impossible debt, we must now dive into the most profound, counterintuitive realm of existence, the quantum vacuum. Forget the classical notion of empty space, a tranquil void where nothing happens. In the quantum world, this seemingly inert expanse is anything but. Here, space-time isn't empty. It's a seething quantum foam, a turbulent ocean of pure potential, perpetually boiling with activity. This is where the universe's audacious trick begins. At this microscopic scale, dictated by the relentless uncertainty of quantum mechanics, particles flicker in and out of existence in fleeting defiance of energy conservation. These are the fabled virtual particles. They are not truly real in the classical sense, in that they cannot be directly observed or measured for extended periods. Yet, their effects are profoundly real and measurable, influencing phenomenon from the Lamb shift in atomic spectra to the Casimir effect, where two uncharged parallel plates in a vacuum experience an attractive force due to the suppression of virtual particles between them. This isn't speculation, it's experimentally verified physics. The key to this cosmic conjuring act lies in Werner Heisenberg's uncertainty principle. It tells us that we cannot simultaneously know with perfect precision both a particle's position and its momentum, or, crucially for our story, its energy and the duration for which that energy exists. This means that for a fleeting moment, a tiny loan of energy can be taken from the vacuum, allowing a particle-antiparticle pair to spontaneously materialize. The catch? This loan must be repaid almost instantly. The more energy borrowed, the faster it must be returned. This is the universe's micro-scale financial system, operating on an infinitesimally brief credit line. This concept of virtual particles and temporary energy loans is the theoretical bedrock for how something could emerge from nothing. The vacuum isn't nothing. It's a teeming reservoir of potential, a cosmic bank offering infinitesimal short-term loans. But how, you might ask? Does a brief subatomic quantum fluctuation lasting for fractions of a femtosecond scale up to a universe 93 billion light-years across, enduring for 13.8 billion years? This is where the theory of cosmic inflation steps onto the stage, transforming a quantum whisper into a cosmic roar. Proposed by visionary physicists like Alan Guth, Andre Linde, and Paul Steinhardt in the early 1980s, inflation posits that in the earliest moments of the Big Bang, a mere 10 to the 36 seconds after its inception, the universe underwent an unimaginably rapid exponential expansion. This wasn't just any expansion. It was driven by a peculiar type of energy density associated with a hypothetical inflaton field. Imagine this inflaton field as a vast primordial ocean of potential energy, existing in a highly unstable state, much like a ball perched precariously on a hill. As this inflaton field rolled down its potential energy landscape, it borrowed an immense, colossal amount of energy from the vacuum. This wasn't a repayment in the traditional sense, it was a conversion. This borrowed energy didn't just vanish. It fueled the staggering exponential growth of spacetime itself, stretching the nascent universe to incomprehensible scales in a blink of an eye. During this inflationary epoch, the universe expanded by a factor of at least 10 to the 26, smoothing out any initial irregularities and flattening its geometry. Then, as suddenly as it began, inflation ended. The inflaton field decayed, releasing its colossal energy, much like a phase transition. This released energy wasn't just dissipated. It was converted into all the matter and radiation that would eventually form the fundamental particles, the first stars, the galaxies, and ultimately us. This decay process is often referred to as reheating, filling the rapidly expanding universe with a hot, dense plasma, the initial conditions for the conventional Big Bang model. So, the debt was repaid, not by returning the energy, but by transforming it into the very substance of reality. Crucially, this inflationary scenario makes several testable predictions. One of the most significant is that the universe should be incredibly flat and homogeneous on large scales. And this is precisely what observations of the cosmic microwave background radiation by missions like COBE, WMB, and particularly the European Space Agency's Planck satellite have overwhelmingly confirmed. The CMB, the faint afterglow of the Big Bang, shows a temperature uniformity across the sky to an astonishing 1 part in 100,000, with subtle characteristic anisotropies, tiny temperature fluctuations that are perfectly consistent with the quantum fluctuations stretched to cosmic scales during inflation. These ripples are the seeds of all structure in the universe. But here's the truly mind-bending part. The ultimate cosmic accounting trick. The universe's total energy, when everything is taken into account, appears to sum to zero. How? The immense positive mass energy of all matter and radiation is precisely balanced by an equally immense gravitational potential energy. Gravity, being an attractive force, creates negative energy. Imagine lifting an object against gravity. You expend positive energy. The object gains potential energy. If you let it fall, it loses that potential energy, converting it to kinetic energy. For the entire universe, if you consider all the matter falling into the gravitational wells of all other matter, that gravitational binding energy is negative. So, the universe, a gargantuan cosmic balance sheet, its existence a perfectly managed loan. It borrowed energy from the quantum vacuum, inflated, and then repaid that debt by converting the borrowed energy into everything we see, simultaneously ensuring that the total energy of the system remains precisely zero. Our reality isn't just a loan. It's a cosmic magic trick where something emerges from nothing, perpetually in perfect self-sustaining balance. But how stable is this magnificent equilibrium? And what does it mean for the ultimate fate of this audacious cosmic enterprise? From that revelation of cosmic equilibrium, where positive mass energy precisely counterbalances negative gravitational potential energy, a profound question emerges. How does the universe maintain this precarious yet seemingly perfect zero-sum game? This isn't merely an elegant mathematical coincidence. It's a fundamental property that underpins the very possibility of existence from nothing. If the universe's total energy truly sums to zero, it means that the cosmic ledger, despite its unimaginable scale, remains perfectly balanced, requiring no external input or prior energy source. Let's dissect this astonishing balance. The positive energy is straightforward. It's the energy equivalent of all matter and radiation, the stars, galaxies, dark matter, photons, neutrinos, and everything else that constitutes the observable universe. Einstein's iconic equation, E equals mc squared, tells us that mass itself is a form of concentrated energy. Every particle, every field contributes to this vast reservoir of positive energy. It's the kinetic energy of moving particles, the rest mass energy of protons and electrons, the radiant energy of starlight, an undeniable, measurable cosmic bounty. But then there's the negative gravitational potential energy. This concept often feels counterintuitive because we usually think of gravity as a force that things to fall, to attract. However, to lift an object against gravity, you must energy to it, giving it positive potential energy. Conversely, when objects fall towards each other due to gravity, their potential energy becomes, the closer they get, the stronger the gravitational pull, and the more negative their potential energy becomes. In a universe where all matter is attracting all other matter, the cumulative gravitational potential energy of the entire system is a vast negative number. It acts like a cosmic debt, pulling everything together. Imagine a universe starting as a single point, or perhaps a fleeting quantum fluctuation. As it expands, matter clumps together, forming stars and galaxies. Each time a particle falls into a gravitational well, whether it's a star forming or a galaxy merging, the system's gravitational potential energy becomes more negative. It's like a cosmic savings account where deposits are offset by withdrawals that precisely keep the balance at zero. The energy required to create all the matter and radiation in the universe is, in this model, precisely offset by the negative energy associated with its gravitational binding. This elegant cancellation has profound implications for the question of origins. If the total energy of the universe is zero, then it requires no net energy input to come into existence. It's the ultimate free lunch, provided the quantum rules allow for the initial borrowing, and the inflationary mechanism can then convert that borrowed energy into the zero-sum reality we inhabit. This isn't merely a theoretical construct, it's a framework supported by multiple lines of observational evidence. The universe's geometry, as measured by the Planck satellite and other CMB experiments, is remarkably flat. In cosmology, a flat universe implies that its total energy density is equal to a critical density. A universe with positive curvature would have a total energy density greater than critical, while a negatively curved universe would have less. A perfectly flat universe, to a very high degree of precision, suggests a universe with a total energy of zero. This observational confirmation provides powerful empirical support for the theoretical models of a zero-energy universe. Furthermore, this balance helps address the flatness problem that inflation was designed to solve. Without inflation, any tiny deviation from perfect flatness in the early universe would have been rapidly amplified, leading to either a universe that immediately collapsed or expanded so quickly that no structure could form. Inflation, by dramatically stretching spacetime, effectively flattens the universe, pushing its geometry towards this critical density, and thus towards a zero total energy state. The precision of this balance is astonishing. If the positive energy of matter and radiation were even slightly greater than the negative gravitational energy, the universe would have expanded too quickly, preventing the formation of galaxies and stars. If the negative gravitational energy were slightly dominant, the universe would have collapsed back on itself long ago, perhaps in a big crunch. The fact that we exist in a universe rich with complex structures is itself evidence of this exquisite, almost miraculous equilibrium. This cosmic balance sheet isn't static, it's a dynamic interplay. As the universe expands, the matter and radiation dilute, but so does the gravitational potential energy. The introduction of dark energy, a mysterious force driving the accelerating expansion of the universe, adds another layer of complexity to this cosmic accounting. While dark energy contributes positive energy density, its pressure is negative, leading to intricate discussions about its role in maintaining or altering this overall zero-energy state.
Current models suggest that even with dark energy, the overall zero-energy balance can be maintained, though the mechanisms are still under active investigation. The implication of a zero-energy universe is profound. It suggests that the cosmos might be a self-contained system, requiring no external creator or initial input of energy. It's simply having emerged from a state that, from our classical perspective, appears to be nothing, yet from a quantum perspective held all the potential for existence. This isn't just about how the universe started, it's about its fundamental nature, its intrinsic stability, and its audacious ability to sustain itself without ever defaulting on its initial impossible debt. But if this balance is so perfect, could it also be eternally stable, or does even a zero-sum game imply a finite lifespan for our cosmic loan?
From the exquisite balance of the universe's zero-sum game, where positive mass energy dances in perfect opposition to negative gravitational potential energy, a new, unsettling question arises. If reality itself is a cosmic loan, however perfectly managed, is its existence inherently temporary? Does even the most meticulously balanced ledger eventually have a final closing date? This isn't about mere cosmological speculation. It touches on the ultimate fate of everything we know, the grand finale of this astonishing cosmic experiment. In the realm of quantum finance, where the universe acts as its own bank, the initial loan of energy was repaid, not by returning it, but by converting it into the vast expanse of spacetime and its contents. The zero-energy universe model suggests a state of perfect equilibrium. But equilibrium, even perfect equilibrium, can be dynamic. The universe is not static, it's evolving, expanding, cooling. The relentless march of the second law of thermodynamics ensures that entropy, the measure of disorder, is always increasing. This cosmic imperative dictates that available energy for work is constantly diminishing, pushing the universe towards a state of ultimate featureless uniformity. So, how might the repayment or default manifest? Early cosmological models, before the discovery of accelerating expansion, often posited a universe that might eventually contract in a big crunch, reversing the Big Bang and collapsing back into a singularity. In such a scenario, the negative gravitational energy would eventually overcome the positive kinetic energy of expansion, pulling everything back together. This would be a dramatic repayment, a cosmic repossession where all assets are liquidated back into their original compressed state. However, current observations, particularly those related to dark energy, suggest a different, perhaps even more chilling ultimate fate. The discovery in the late 1990s that the universe's expansion is not slowing down, but accelerating, driven by the mysterious dark energy, fundamentally altered our understanding of the cosmic balance sheet. Dark energy, a form of energy inherent to space-time itself, acts as a repulsive force, pushing galaxies further apart at an ever-increasing rate. While it adds positive energy density to the universe, its unique properties complicate the simple positive-negative energy balance, yet don't necessarily negate the zero-energy principle. Many theoretical models of dark energy still allow for a universe with zero total energy, albeit one whose expansion history is vastly different from a decelerating cosmos. If dark energy continues its relentless acceleration, the most widely accepted ultimate fate is the heat death or big freeze. In this scenario, the universe expands indefinitely, diluting matter and radiation to extreme levels. Stars will eventually burn out, black holes will evaporate through Hawking radiation, and the entire cosmos will become a cold, dark, empty expanse, where the temperature approaches absolute zero and no further thermodynamic processes can occur. This isn't a dramatic repayment, but a slow, agonizing dissolution, where the cosmic loan simply dissipates into an indistinguishable, featureless void. It's a repayment by exhaustion, where all the value of the loan is spread so thin it ceases to be meaningful.
Alternatively, some more extreme dark energy models suggest a big rip, where the accelerating expansion becomes so powerful that it tears apart galaxies, stars, planets, and even atoms themselves, literally ripping the fabric of spacetime apart. This would be a catastrophic default, a complete unraveling of the cosmic collateral. The question then becomes, is there a cosmic interest rate on this loan? If the universe is a temporary fluctuation, how long can it sustain itself before the quantum bank calls in its markers? Current estimates suggest the universe has many billions, even trillions of years before any of these ultimate fates play out. But the very concept that our reality, with all its complexity and beauty, might be a transient phenomenon, a grand illusion built on a temporary loan, is profoundly humbling. Frontier physics is actively exploring the stability of this cosmic balance. Researchers are looking for subtle deviations from the CMB, refining measurements of dark energy's equation of state, and searching for evidence of extra dimensions or exotic fields that could influence the universe's ultimate destiny. Experiments like the Dark Energy Survey, the upcoming Euclid mission, and the Square Kilometer Array are meticulously mapping the large-scale structure of the cosmos to understand the interplay of matter, gravity, and dark energy. Could there be a deeper cyclical nature to this cosmic borrowing? Some theories, like the cyclic universe model proposed by Paul Steinhardt and Neil Turok, suggest that our universe is just one in an infinite series of big bangs and big crunches, with each cycle emerging from the ashes of the previous one. In this view, the debt is perpetually rolled over, never truly repaid, but simply transformed into the conditions for the next cosmic iteration. This would transform the temporary loan into an eternal, self-renewing credit line, a universe that constantly reinvents itself. The implications are staggering. If reality is a loan, then our existence is an extraordinary, fleeting moment of borrowed time, a brief, vibrant flash against an eternal backdrop of quantum potential or ultimate cosmic stillness. It shifts our perspective from a universe that, to a universe that, to a universe that. What does it mean to be alive, to observe, to understand, if the stage itself is destined to fade? This forces us to confront the profound fragility and preciousness of our cosmic moment. The question shifts from when the universe began to how long this grand illusion can persist. Is there an ultimate cosmic debt collector, or is the balance so perfectly managed, so inherently self-sustaining, that our cosmic loan is in effect eternal, simply changing forms? The answer lies at the intersection of quantum gravity, cosmology, and the deepest mysteries of space-time itself, urging us to continue our relentless exploration of the universe's audacious financial strategy. From the potential transience of our cosmic loan, where the universe's meticulously managed balance hinted at possible ultimate fates, we arrive at a final, breathtaking reflection: the sheer audacity of existence itself. We've journeyed from the impossible paradox of a universe emerging from absolute nothingness, through the quantum realm's audacious borrowing, the inflationary repayment, and the meticulous zero-sum balance of positive mass energy against negative gravitational potential energy. This isn't just a story of beginnings, it's a profound narrative about the very nature of reality. A testament to the universe's capacity for self-creation, a grand symphony conducted without an initial score. The universe, in this astounding scientific narrative, didn't require an external catalyst or an initial funding source. Instead, it appears to be a magnificently self-contained entity, a cosmic system that bootstrapped itself into being, operating on an internal logic far more intricate and elegant than classical physics ever dared to imagine. The quantum vacuum, once considered an inert, empty expanse, is revealed as a vibrant, seething crucible of potential, brimming with virtual particles. Here, temporary energy fluctuations, governed by the Heisenberg uncertainty principle, provide the initial spark, the infinitesimal quantum loan that kickstarts creation.
These fleeting credits are then leveraged by the immense, expansive power of inflation, which rapidly stretches and cools the nascent cosmos, converting that borrowed energy into the raw materials of stars, galaxies, and eventually life itself. The genius of this cosmic accounting lies in the precise cancellation of energies. The vast amount of positive energy embodied in all the matter and radiation, the luminous galaxies, the swirling nebulae, the very atoms of our bodies, is perfectly offset by an equally immense reservoir of negative gravitational potential energy. This intricate balance, confirmed with astonishing precision by the extraordinary flatness of the universe observed in the cosmic microwave background, allows the universe to maintain a net energy of zero. It's the ultimate sleight of hand, a cosmic magic trick where the greatest show on Earth and beyond performs without a net, without a visible source, simply by balancing its own books. The cosmos, in its grandest gesture, is forever solvent, its impossible debt perpetually managed. This understanding profoundly redefines our concept of nothing. It's no longer the inert void of classical thought, but a dynamic, pregnant state brimming with latent possibilities, waiting for the quantum dice to roll. It forces us to reconsider the very nature of non-existence, transforming it from an absence into a fertile ground for creation. And it challenges our very notions of causality, suggesting that the universe might be its own cause, its own explanation, a self-referential loop of existence that simply... This isn't to say we have all the answers. Far from it. The precise nature of dark energy, the elusive mechanisms of quantum gravity, and the ultimate fate of this perfectly balanced system remain active frontiers of discovery, beckoning the next generation of scientific explorers. But the framework itself offers a coherent, scientifically rigorous explanation for the ultimate question that has plagued humanity for millennia. Why is there something rather than nothing? The universe, in essence, is the ultimate free lunch, a grand, self-sustaining illusion of something from nothing, forever in perfect, dynamic balance. We, as conscious observers, are privileged witnesses to this audacious act of cosmic self-creation, a fleeting yet magnificent manifestation of borrowed energy, continuously managed and perpetually in equilibrium. Our existence is not just a biological miracle born from stardust and chemical reactions, but a cosmic one, emerging from the quantum foam and destined to explore the very depths of its impossible origins. To gaze at the night sky, knowing that every shimmering point of light, every colossal galaxy, every whisper of dark matter might be a manifestation of this cosmic IOU, is to feel an awe that transcends mere wonder. It's to understand that our reality, with all its breathtaking complexity and beauty, is the most magnificent, improbable, and audacious loan ever conceived. This grand narrative, still unfolding through the tireless work of physicists and cosmologists, stands as a testament to the boundless ingenuity of the cosmos and the relentless human spirit that strives to comprehend its deepest secrets. It reminds us that at the frontier of science, the universe continues to reveal itself as a place of unimaginable mystery and profound elegance, a reality that, against all classical odds, simply a cosmic masterpiece born from an impossible debt that paradoxically funds everything. We are part of this extraordinary cosmic calculus, living proof of the universe's ultimate financial alchemy. The journey to understand continues, always pushing the boundaries of what we thought possible, forever chasing the echoes of creation's first impossible transaction.